In this video, I'll briefly describe seasons and timekeeping. I've covered these topics in much more detail on Cosmic Time. Seasons are caused by the tilt of the Earth. When we say the Earth has a tilt, what we mean is that its rotational axis, which is an imaginary line that goes through the South Pole and the North Pole, is tilted relative to its orbital plane, which is defined by Earth's path around the Sun. Some planets have a tilt, others don't. Uranus has an extreme tilt that's close to 90 degrees. Earth has a moderate tilt, around 23.5 degrees. When our hemisphere is tilted towards the Sun, we experience summer. When it's tilted away, we experience winter. When it's tilted sideways or perpendicular to the Sun, we experience spring or fall. This means that when it's summer in the northern hemisphere, it's winter in the southern hemisphere, and vice versa. And when it's spring in the northern hemisphere, it's fall in the southern hemisphere. When our hemisphere is tilted towards the Sun, we have long days and short nights, and when it's tilted away, we have short days and long nights. The longest day of the year is called the summer solstice. It occurs on June 20th or 21st in the northern hemisphere and around December 21st or 22nd in the southern hemisphere. The dates shown here are not exactly right. All four of these special dates do not occur on the 21st of the month. Again, when it's the summer solstice for us, it's the winter solstice for people in Brazil, South Africa, and Australia. On the equinox days, we have 12 hours of day and 12 hours of night. These occur on March 20th and on September 22nd or 23rd. One reason it's hotter in the summer than in the winter is simply that there are more daylight hours in the summer. During the summer, the ground has more time to soak up the sun's heat and less time to release it. The other, more important reason it's hotter in the summer is that the sun gets higher in the sky, and so the intensity of sunlight is greater. When the sun is high in the sky, its light is more concentrated, as shown on the left. When the sun is low in the sky, its light is more spread out, as shown on the right. Of course, it's the same reason it's usually hotter in the middle of the day than in the morning or evening. So in summary, the underlying cause of seasons is the tilt, but it has two effects: more intense sunlight during the summer and more daylight hours in the summer. Notice what I didn't mention: distance. It is true that the Earth has a slightly elliptical orbit, and so it's slightly closer to the Sun at some times than at other times. But that change in distance is too small to affect the seasons. The change in distance due to the tilt itself is even smaller. It's not that the tilt brings us closer to and further away from the Sun. It's just that the angle of the sunlight and the number of daylight hours are more during the summer than in the winter. Since we're stuck here on Earth, we don't get to directly see the tilt of the Earth relative to the Sun. Instead, we see the Sun drift northward and southward throughout the year. The figures here show the Sun moving across your sky on the solstices and equinoxes. The orange plane is the ground. The edge of this plane is called the horizon. That's where the sky meets the ground. Again, the tilt of the Earth is 23.5 degrees. So if you're between the latitudes of 23.5 degrees north and 23.5 degrees south, the sunlight will hit you directly at some point, and you'll see the sun at the top of the sky, which is called the zenith. The region between 23.5 degrees north and 23.5 degrees south is called the tropics. Chicago's latitude is 42 degrees north, so we're well outside the tropics. This means you'll never see the sun at the zenith, at the top of the sky, from Chicagoland. Here, the sun is in the southern part of the sky at noon every day. The sun rises in the east, but not due east every day. In the summer, as shown on the left, it rises in the northeast and sets in the northwest. But at noon, it's high in the south. On the equinoxes, as shown in the middle, the sun rises due east and sets due west, and is again in the south at noon, but not too high, not too low. In the winter, as shown on the right, the sun rises in the southeast, is low in the south at noon, and sets in the southwest. So it stays in the southern part of the sky all day during the winter. That's why it's good to have big south-facing windows here at mid-northern latitudes. They let in the sunlight during winter. If you have an overhang above the window, that's even better because it would block the sunlight during the summer when the sun is high in the sky, but not in the winter when the sun is low in the sky. Here is another view. It's similar to the first diagram, which showed the Earth orbiting the sun, except that this one is zoomed in on the Earth at one particular time, which is the northern summer solstice. The northern hemisphere of the Earth appears to be tilted towards the sun. The sun is very far away, and so it's not shown. 3 rays of sunlight are shown instead. The sun is in the direction of the middle ray, but way beyond the screen to the left. So the direct rays of sunlight are shining on the Tropic of Cancer, which is at a latitude of 23.5 degrees north. This is the furthest north the direct rays of sunlight will get. This is 6 months later. The northern hemisphere is now tilted away from the sun. The direct rays of sunlight are now shining on the Tropic of Capricorn, which is at a latitude of 23.5 degrees south. So this is the winter solstice in the northern hemisphere and the summer solstice in the southern hemisphere. As I've explained in detail on Cosmic Time, what we call a day is based on the position of the sun in the sky. It's not exactly 1 360-degree rotation of the Earth. This figure illustrates the difference. On day 1, at the time shown, it's noon for this enormous red person. As the Earth turns, it also moves slightly in its orbit around the sun. 1 day later, it's moved a bit. 360 is pretty close to 365, so it moves around 1 degree per day. After the Earth has completed a full rotation, it's actually not noon for our person yet. It will take another 4 minutes for it to be noon. So 1 rotation of the Earth actually takes 23 hours and 56 minutes. You'll see that if you use a much more distant object than the sun, like a star, as your reference point. So stars rise roughly 4 minutes earlier each night. Our 24-hour day is roughly the time from noon to noon. People have been obsessed with the sun, moon, planets, and stars for millennia. Our day and year are based on the sun. The month is based on the moon. The days of our week are named after the sun, moon, and 5 visible planets. There are even calendars based on star positions. Ancient societies built impressive structures that appear to line up with these heavenly bodies. The pyramids of Giza in Egypt, for instance, like the streets of many ancient Egyptian cities, were perfectly aligned with the cardinal directions, north, south, east, and west. And so you could use the pyramids to track the equinoxes. Around the same time, people in present-day England were erecting large slabs all over the place, including famously at the place we now call Stonehenge. Archaeoastronomers have been studying and debating how the stones are aligned with the sun during the solstices and with the moon at its extreme rising and setting points. Here are a couple of monuments at the Mayan archaeological site of Chichen Itza in Mexico. Like the Giza pyramids, this pyramid is perfectly aligned with the cardinal directions. So at sunset on the equinoxes, Kukulkan, the serpent, appears. The head of the serpent is at the base of the staircase. The rest of the serpent is formed by the shadows of the steps on the staircase. The building on the right is called El Caracol. There are strong indications that this was actually a Venus observatory. The Mayans used 3 different calendars: a 365-day solar calendar, a 260-day calendar which has no parallel elsewhere in the world, and also a 584-day Venus calendar. The skylights of this building appear to be aligned with the extreme rising and setting points of Venus. These are just a few examples of alignments between heavenly bodies and ancient monuments. Such things are found all over the world, and so we couldn't possibly do full justice to them in this course. If this is a topic that interests you, I can share with you some resources.